Torchsparsecootensor. Description. The torchsparsecootensor function creates a sparse tensor in the coordinate COO format. Sparse tensors are used to efficiently represent data with mostly zero values. In the COO format, a tensor is represented by three tensors indices, values, and size. Indices: a 2D tensor containing the indices of non-zero elements in the sparse tensor. Each row represents the indices of one non-zero element. Values: a 1D tensor containing the values of the non-zero elements in the sparse tensor. Size: a 1D tensor defining the size of the sparse tensor. Inputs: indices: a 2D tensor containing the indices of non-zero elements in the sparse tensor. Each row represents the indices of one non-zero element. Values: a 1D tensor containing the values of the non-zero elements in the sparse tensor. Size: a 1D tensor defining the size of the sparse tensor. D-type optional: the desired data type of the sparse tensor. Device optional: the desired device for the sparse tensor. Requires grad optional: whether to track gradients for this tensor. Outputs: sparse tensor: a sparse tensor in COO format. Steps: the torchsparsecootensor function takes the indices, values, and size tensors as input. It constructs a sparse tensor in the COO format using these tensors. The resulting sparse tensor represents the data in a compressed way, storing only the non-zero elements and their corresponding indices. Challenges and fixes. Challenge 1: duplicate indices. If the indices tensor contains duplicate rows, the torchsparsecootensor function might produce unexpected results. This is because duplicate indices lead to ambiguity in the value assignment. Sample use case: Python. Indices: torch, tensor 0, 0, 1, 1, 0, 0. Values: torch, tensor 1, 2, 3. Sparse tensor: torchsparsecootensor indices, values, size 2, 2. Fixes before constructing the sparse tensor. Ensure that the indices tensor does not contain duplicate rows. If it does, you can remove the duplicates or adjust the values tensor accordingly. Challenge 2: incorrect size. If the size tensor does not correctly represent the size of the sparse tensor, the resulting sparse tensor might have unexpected behavior. This is because the size tensor dictates the dimensions of the sparse tensor. Sample use case: Python. Indices: torch, tensor 0, 0, 1, 1. Values: torch, tensor 1, 2. Sparse tensor: torchsparsecootensor indices, values, size 2, 1. Fixes: make sure the size tensor accurately reflects the desired size of the sparse tensor. Adjust the size tensor if necessary. Challenge 3: inconsistent shape. The indices and values tensors must have compatible shapes. The number of rows in the indices tensor should match the length of the values tensor. Sample use case: Python. Indices: torch, tensor 0, 0, 1, 1. Values: torch, tensor 1, 2, 3. Sparse tensor: torchsparsecootensor indices, values, size 2, 2. Fixes: ensure that the indices and values tensors have compatible shapes. You can adjust either tensor or use slicing to achieve compatibility. Torchsparsecootensor. Description. The torchsparsecootensor function creates a sparse tensor in the compressed sparse row CSR format. CSR is an efficient representation for sparse matrices where only the non-zero elements are stored. Inputs: cootensor: a p-torch sparse tensor in the COO coordinate format. This tensor represents the sparse matrix where each non-zero element is specified by its row and column indices along with its value. D-type optional: the data type of the elements in the CSR tensor. If not specified, the data type of the input cootensor is used. Device optional, the device CPU or GPU where the CSR tensor should be stored. If not specified, the device of the input cootensor is used. Outputs: CSR tensor, a p-torch sparse tensor in the CSR format. It represents the same sparse matrix as the input cootensor but in a compressed and efficient representation. The CSR tensor stores three arrays. Row indices, an array of integers representing the starting row index for each row in the sparse matrix. Colindices, an array of integers representing the column indices of the non-zero elements in a sparse matrix. Values, an array containing the values of the non-zero elements in the sparse matrix. Steps: the torchsparsecootensor function first sorts the non-zero elements in the input cootensor by their row indices. It then constructs the row indices array by identifying the starting index of each row in a sorted non-zero elements. The colindices array is created by simply extracting the column indices of the sorted non-zero elements. Finally, the values array is populated with the corresponding values of the sorted non-zero elements. Challenges and fixes. Challenge 1: the input cootensor is not sorted by row indices. Sample use case: a sparse matrix where the non-zero elements are not arranged in ascending order of row indices. Fixes: sort the input cootensor by row indices before passing it to torchsparsecootensor. Challenge 2: the input cootensor contains duplicate row column indices. Sample use case: a sparse matrix where multiple non-zero elements share the same row and column index. Fixes: before converting to CSR, remove duplicate entries from the input cootensor by aggregating their values. Torchsparsecootensor. Description: the torchsparsecootensor function constructs a sparse tensor in compressed sparse column CSC format. It uses three tensors to represent the sparse matrix. Indices: this tensor stores the row indices of the non-zero elements. Values: this tensor stores the values of the non-zero elements. Columns: this tensor stores the column indices of the non-zero elements. The CSC format is commonly used in linear algebra and numerical analysis for efficient storage and computation of sparse matrices. Inputs: indices: a 1D tensor of type torch, long that stores the row indices of the non-zero elements. The shape of this tensor should match the number of non-zero elements. Values: a 1D tensor of the desired data type that stores the values of the non-zero elements. The shape of this tensor should match the number of non-zero elements. Columns: a 1D tensor of type torch, long that stores the column indices of the non-zero elements. The shape of this tensor should match the number of non-zero elements. Size: a 2-tuple containing the desired shape of the resulting sparse tensor. This specifies the number of rows and columns of the sparse matrix. Outputs: sparse tensor: a sparse tensor of type torch, sparsecootensor representing the sparse matrix. Steps: the torchsparsecootensor function takes the indices, values, and columns tensors as input, along with the desired size of the sparse tensor. It uses these inputs to construct a sparse tensor in CSC format, where the non-zero elements are organized by columns. The indices tensor specifies the row indices of the non-zero elements. The values tensor stores their corresponding values, and the columns tensor defines the column indices of the non-zero elements. Challenges and fixes. Challenge 1: the input tensors must be of the correct type torch, long for indices and columns, and the desired data type for values. Sample use case that resulted in challenge 1. Passing a tensor of type torch, float for indices or columns. Fixes to challenge 1. Ensure that the indices and columns tensors are of type torch, long. Challenge 2. The shapes of the input tensors should be consistent indices. Values and columns should all have the same length, and it should match the number of non-zero elements in the sparse tensor. Sample use case that resulted in challenge 2. Providing an indices tensor with a different length than the values tensor. Fixes to challenge 2. Ensure that all three input tensors indices, values, and columns have the same length. Challenge 3. The size argument should be a two-tuple specifying the number of rows and columns of the sparse matrix. Sample use case that resulted in challenge 3. Passing a single integer value for size. Fixes to challenge 3. Provide a two-tuple for the size argument, representing the number of rows and columns of the sparse matrix. Torch-sparse tensor. Description. The torch-sparse tensor function is used to construct the sparse tensor in the block sparse row BSR format. This format is specifically designed for efficiently storing and manipulating sparse matrices with blocks of non-zero elements. Inputs. Cootensor. This is a p-torch sparse tensor in the coordinates COO format. The COO format represents the sparse tensor using three tensors indices, values, and size. The indices tensor contains the row and column indices of the non-zero elements. Values holds the corresponding values, and size specifies the dimensions of the sparse tensor. Block size. This argument is an integer tuple specifying the size of each block in the BSR format. For example, block size 2 would create blocks of 2 rows by 2 columns. The default value is 1, which effectively creates a sparse tensor in the compressed sparse row CSR format. Outputs. Sparse BSR tensor. This is the resulting sparse tensor in the BSR format. It stores the sparse matrix as a tuple of 3 dense tensors crow indices, col indices, and values. Crow indices. This tensor represents the starting indices of each row block in the values tensor. Col indices. This tensor contains the column indices of the non-zero elements within each block. Values. This tensor stores the non-zero values of the sparse matrix organized by row blocks. Steps. Conversion from COO to BSR. The function first converts the input COO tensor to the BSR format. This involves grouping non-zero elements into blocks based on the specified block size. Block indexing. The crow indices and col indices tensors are generated to represent the block structure of the BSR format. Crow indices indicates the starting position of each row block in the values tensor, while col indices maps the column indices of the non-zero elements within each block. Value organization. The non-zero values from the COO tensor are arranged into the values tensor based on the block structure. Challenges and fixes. Challenge 1. Choosing the optimal block size. The choice of block size can significantly impact the performance of operations on the sparse tensor. Selecting too small a block size might not provide enough memory efficiency, while a too large block size could lead to increased computation overhead. Sample use case that resulted in challenge 1 in a sparse matrix with a highly irregular structure. Choosing a small block size might lead to inefficient storage and computations. On the other hand, if the matrix has large blocks of non-zero elements, a large block size could be more beneficial. Fixes to challenge 1. The optimal block size depends on the specific characteristics of the sparse matrix. Experimentation with different block sizes and analysis of performance metrics, e.g. memory usage. Computation time can help determine the best configuration. Challenge 2. Handling sparse matrices with inconsistent block sizes. If the input sparse matrix has blocks of non-zero elements with varying sizes, torchsparsecootensor tensor will still create blocks based on the specified block size. This can lead to empty blocks or blocks with incomplete elements. Sample use case that resulted in challenge 2. If the input sparse matrix has blocks of varying sizes, e.g., some blocks are 2 by 2, while others are 3 by 3. Using a fixed block size, e.g., 2 will result in some blocks being incomplete. Fixes to challenge 2. For such scenarios, it is recommended to pre-process the sparse matrix to ensure consistent block sizes or use alternative sparse formats like COO, which are more flexible in handling variable block sizes. Torchsparsecootensor. Description. Inputs. Indices: a 2D tensor of shape num non-zeros. 2. Containing the row and column indices of the non-zero elements. Values: a 1D tensor of shape num non-zeros. Containing the values of the non-zero elements. Size: a 2D tensor of shape 2. Containing the size of the sparse tensor. A sparse tensor in the BSC block sparse column format. Steps. The function takes 3 inputs: indices, values, and size. The indices input specifies the row and column indices of the non-zero elements. The values input contains the values of the non-zero elements. The size input specifies the size of the sparse tensor. The function then constructs a sparse tensor in the BSC format using the provided inputs. The BSC format is a compressed format for sparse tensors that stores the non-zero elements in a column-wise manner. Challenge 1. The indices input must be sorted in column major order. Sample use case that resulted in challenge 1. If the indices input is not sorted in column major order, the resulting sparse tensor will be incorrect. Fixes to challenge 1. Sort the indices input in column major order before constructing the sparse tensor. Challenge 2. The size input must be a 2D tensor of shape 2. Sample use case that resulted in challenge 2. If the size input is not a 2D tensor of shape 2, the function will raise an error. Fixes to challenge 2. Ensure that the size input is a 2D tensor of shape 2. Challenge 3. The number of non-zero elements in the values input must be equal to the number of rows in the indices input. Sample use case that resulted in challenge 3. If the number of non-zero elements in the values input does not match the number of rows in the indices input, the function will raise an error. Fixes to challenge 3. Ensure that the number of non-zero elements in the values input is equal to the number of rows in the indices input. Challenge 4. The values input must be a 1D tensor. Sample use case that resulted in challenge 4. If the values input is not a 1D tensor, the function will raise an error. Fixes to challenge 4. Ensure that the values input is a 1D tensor. Challenge 5. The indices input must be a 2D tensor of shape num non-zeros. 2. Sample use case that resulted in challenge 5. If the indices input is not a 2D tensor of shape num non-zeros. 2. The function will raise an error. Fixes to challenge 5. Ensure that the indices input is a 2D tensor of shape num non-zeros. 2.